So good morning, everyone. I'm Rhett Davis from North Carolina State University. I'm going to talk about how we have used the ARM kits in teaching as well as our research program and some of our perspectives on that and why we use it. I'm going to present, this is work I've done in collaboration with, oops, does that work? Nope, no, that's okay. I've done in collaboration with my colleagues Eric Rotenberg and Paul Franzen at NC State, so I want to make sure they get credit for this stuff as well. And then I've listed all of the graduate students who have been involved in this. So if you don't know me, I like making chips, but I'm not just interested in making any chips. I'm really interested in making chips that work, which kind of makes me unusual for an academic. I find that once you get above about 100,000 gates, the chips that work in an academic setting anyway are the exception rather than the rule. And you know, that's kind of okay. If you're doing architecture research, you can still learn an awful lot from making a chip that doesn't work. So I don't want to poo-poo that too much. But if you're like me, and what you're interested in is the design process and the design methodology and the design flows, then having a chip that doesn't work is kind of useless to you, because how do you know whether actually if the chip doesn't work, then the flow that was used to make it is uninteresting. So that kind of gives you a framework to understand where I'm coming from in using the ARM tools and the ARM IP rather. So let's think in terms of the kind of system that I'm very interested in building, which has been mentioned a fair bit here yesterday, which is 3D stacking of systems. I've got a picture of an AMD high bandwidth memory, which I'm just kind of including because I love the picture, which is sort of indicative of the sorts of things that we're trying to prototype, as well as a conceptual stack from a project that we were doing at NC State that I'll talk about here in a minute. You've got benefits of heterogeneous integration, so having DRAM integrated with the logic. You can also get benefits from miniaturization, shorter wires. These are the different kinds of things that we're interested in research projects showing an advantage from. So the real big question that has been burning me up is, how do we make this easier to prototype? How do we make this easier in a university setting to prototype things that work to show our value? And I've included my conclusion slide here because I know that I'm standing between you and a coffee break. So to make it short and sweet, what's the main message that I'm trying to get across? And so the first is that, well, what makes it hard is essentially complexity. And that means that you've got lots of cells, and also lots of behavior, which makes it very difficult to know how much power they're going to dissipate, how fast they're going to run. That means that in the design process, and I'm thinking mostly of the physical design process of taping it out, as well as the coding up of the RTL source files that make it all work. You've got very long run times for simulation as well as place and route. You've got huge files, and so that makes this process very complicated. So now if you think of the little neural net, another popular topic in the last couple of days, that each designer has to run in their mind, that essentially runs down to few samples. So you're trying to get this very complex process to work with very few trials. And we could even think of actually building, machine learning tools to help this process. But if you have very few samples, that's very few opportunities to get it right. And that's essentially the problem with getting all this to work. So that leads to uncertainty, well, depending on how you look at it, uncertainty or inaccuracies. You don't really know whether the circuit is going to be working as you expect. So why does ARM IP help us with this? And the main thing is that it just works, that in these state-of-the-art debugging flows and design flows. So that means that we spend little or no time actually trying to solve problems with our design, and we can spend all of our time debugging the flow to figure out how to mitigate these problems that I mentioned. Because so often when we do these large designs, we can spend days or weeks trying to track down a particular problem, only to find that it was a problem with the design that we have created rather than the flow, that the flow is actually working properly. So it helps us to separate those concerns. And it does that with a consistent organization and management of the complexity of the whole system, and helps us to separate these good design flow tweaks from the bad ones. So that, in a nutshell, is why we use it. So let's see, how are we doing? Given that we only have like about 8 minutes to talk about the rest, and I have about 15 more slides, let me just give you a quick flavor for this, and really try hard not to go into the details, but to give you some slides, so that if you want to ask me about the details, you can. So first, one slide about how we use it in teaching, because that sort of drives everything else, and then just a little bit about 3 different research projects where this comes in. So here is, in one slide, is sort of a picture of the system that we use in a course called Electronic System Level and Physical Design, where we go all the way from an ESL transaction level modeling view of a system down to the physical design and verification at the signal integrity and power integrity level. And it's all done in one semester. We use this ARM-based SoC to do it, which is built around a Cortex-M0 DesignStart processor, as well as Synopsys bus and memory controller models. And then the goal is for them to build an accelerator that sits on the system, and then to show the whole system working, again, from the highest level of abstraction to the lowest. It's got about 20,000 gates total, which is enough to sort of force them into this very structured methodology where they don't have time to really hack things, but they have to observe this very careful methodology and show the whole thing working. It allows them to sort of see how their estimates of power, performance, and area change from that highest level of abstraction all the way down to the bottom, so that they're used to seeing that certainty grow rather than sort of becoming less certain, and so that you can converge on a finished system. So we also use ARM fast models, which is that transaction level modeling environment. And I'm hoping that will soon become part of the educational offering. And one day, hopefully, we will also incorporate this into the synthesis scripts so that you can actually place and route designs. Things have to change before that works. We have to get agreements to use these kinds of tools and these standard cell libraries in an education environment, but that's all things that we're working towards. So that, in a nutshell, is what we use. Just a couple things about 3 projects. One, and probably the one that was my favorite, which I'm going to have to try the hardest not to talk forever about, is one where we actually built this 3D stacked microprocessor. We had a stack with using face-to-face bonds with a high-performance big core on the top, a low-performance small core on the bottom. There are some details about it. It used about 1.5 million gates. It was the biggest design that I've ever worked on. Actually, I've joked with the research guys when I was talking about this before. It's kind of more of a big core and a slightly less big core. So we can talk about that more offline. And it used a MIPS ISA. So this was a design that was driven by Eric Rotenberg in our department. Now, of course, why am I talking about how ARM helped us if these used a MIPS ISA? And well, that wasn't part of my part of the project. That was Eric Rotenberg's part. But the main reason why I bring up ARM here is that we had to use the ARM SoC to debug the flow. That we had to build an entire physical design flow using mostly industry tools with a few point tools to stitch them together into this 3D stacking environment, as I described there. And of course, we started out with about 100 gates to show that it was working, and then they throw in the 1.5 million gate system, and it just doesn't work. So what do we do to fix it? Well, the first thing that they did was, having taken this ESL and physical design course, they throw in the Cortex-based SoC, and they debug the whole flow, getting it to work there. And I really don't know if the chip would have ever worked if we had not done that, because we debugged so many problems with the flow by using the Cortex SoC to drive it. that it was really a lifesaver for us. And the experience of having had the class really sort of raised the expectation in them to do it that way, and that's, I think, why it worked out. It also allowed us to do some other interesting tests, which I won't go into here, looking at the benefits of the relative benefits of via pitch, as well as looking at different floor planning strategies, reminiscent of the thing that the gentleman from Synopsys talked about yesterday in terms of technology and architecture co-optimization. It made all of those sorts of things possible for us. I'll also talk a little bit about our measurement results. Again, the main purpose of mentioning all this is that because of the ARM IP, which helped us to debug the whole flow, it raised this expectation and it enabled all of these measurement results, which I don't know that would have been possible had we not had that experience. And we showed that we could migrate a thread within 100 cycles from one core to the next. We also showed that a crisp quantification of the ultimate benefit, which was that by having this heterogeneous stack, we were able to get slightly less energy than using just a single large core, or slightly less energy than, sorry, what am I saying here? Less energy. This is where I get tripped up because I'm not the computer architect. Right, so the two-wide was, we want to show that for this range of benchmarks that we can use less energy than by just having the large core, but by migrating certain parts of the program to the smaller core, we can actually get a smaller amount of energy. Also, if we just had the small core, the one-wide, that we could get a faster execution by migrating parts of it to the two-wide core. And so we were able to show that by having the stack, we could sort of get something that was better than having either one, and that was the main research goal. So it was successful, and again, was thanks to having that ARM IP that it was successful. So now moving this on into saying, well, what if we really did want to have a machine learning algorithm to do this kind of physical design for us? Now that we have this very structured approach, we can start to talk about putting a machine learning loop around this to sort of figure out, well, how can we, instead of training our own neural nets or having the physical designers train their personal neural nets to figure out how to put together this physical design flow, can we turn our physical designers into trainers and say, now don't just do the button pushing yourself, but become the trainer that trains the machine learning algorithm to push those buttons for you and explore to find the best path through the physical design flow. So that's another project that we have going on now. It's funded by this machine learning research center that we have with Georgia Tech and Illinois. Again, I don't want to talk too much about that. I will show you one picture here, which was the picture that we get more traction with than probably any other, which was a simple experiment that was done by one of our PhD students, Wei-Yi Chi, who showed that by putting a very simple machine learning algorithm outside this flow, that he was able to build a surrogate model for how the system should work that allowed him to do basically in 4 iterations what it otherwise took him 17 iterations to do. I think that's what he said. 20 iterations, no. So he did within 4 iterations what it took another designer 20 iterations to do. Because rather than just randomly trying spots and knobs, the surrogate model figured out what the best settings were, or rather, a predictable amount of settings, and then allowed him, it didn't completely remove the designer from the loop, but made him more efficient. And of course, what did he use to drive this? Well, you guessed it, it was that same Cortex SoC that we used from the class. And so if we hadn't had that, and if it hadn't been debugged and working, there's no telling whether or not he would have ever had success with this. And now we are doing more studies with this. We are doing research in machine learning to try to figure out, well, how many samples do we need of these different designs to try to figure out what the range of possible designs are? How do we optimize that? What machine learning algorithms, what models are the best ones to handle the sort of the random behavior of the tools and the difficulty of understanding this complex behavior? And as you might guess, the Cortex SoC, as is shown on the right here, is always the one that is sort of our pipe cleaner, if you will, to make sure that everything is working. We quite often find that many of the samples that go through this are just bad, of course, because it's very complex and because it's very error-prone. And the way that we always know which ones are bad or are not is that we compare it to the Cortex and we say, is it working as well as that one? And if not, then we know that there's something we have to go and figure out. So that is, we're just about out of time, but let me just mention one last thing, which is universal power models, which is something that's also very close to my heart, which is just looking more towards the future, looking at bigger picture issues of computer architecture. I think that one of we all say that we want system level power models, and one of the reasons that those are so pressing to be able to analyze power at the system level is because of the need for reliability. These parts wear out. And there's interesting research that I've referenced here from 2014 of people looking at how do you optimize the way that you schedule and distribute workloads and power so that you can actually make sure that these systems don't wear out. In fact, you see that there's different failure mechanisms that are exposed based on how different parts of your chip heat up. And I would encourage you to read that paper if you're interested in more about it. But where I'm coming at this from is the problem that all of the research that's out there in temperature reliability co-optimization is based on unreliable power models. And the problem with that is that if your power model is unreliable, then I think your co-optimization is also going to be unreliable. And the reasons for that, I've just got sort of two images here that illustrate why they're unreliable. The first is, on the middle there, is showing how the leakage power estimates are unreliable. First, that if you just were to look at how a NAND gate leaks relative to an inverter over a full range of process voltage and temperature variations, then you find that there are some cases where they differ by a factor of 60. And so if your leakage powers can differ by a factor of 60, or maybe they're about the same, then how do you know how much leakage power you really got? Then dynamic power on the right. The behavior of these systems is so complex, it's very difficult to know how much dynamic power they're consuming at any point in time. So, and all of the reliability mechanisms are essentially based on this Arrhenius equation, which shows how temperature basically has this exponential variation with, the reliability mechanisms vary exponentially with that temperature, and temperature, of course, depends on power, so you have to have more accuracy there. So this is why I've been very heavily involved with different IEEE standards organizations, in particular the IEEE P2416 group, which ARM is involved with. And we need to create examples to help move the standard forward. And the ARM SoC has always been the example that we use to create examples to help inform the committee. I've got some of the plots that we have shared with the committee to drive this forward. And one of the interesting questions that always comes up is, well, would it be easier to just have me keep creating the examples, or would it be better to diversify the effort among the standards committee and use an open source processor like the RISC-V or this MIPS example that we have up at the top that I mentioned initially, and that way we could have an open platform for which everyone could share and look at the results. But what we keep finding step after step after step is that it's the effort that's required to use those open platforms is so huge that we just make so much more progress by just using the ARM IP and just having me all do it myself, that I don't know that we would have ever gone as far as we've gotten if we hadn't used the ARM IP. So that is where I will stop it, and we can go get some coffee. Thanks for your attention. Although I will leave you with one fun thing here and one reminder, which is to always be skeptical of your intellectual property, and I'll ask for a quick show of hands here. So which one of these is the real dye photo? Is it the one on the right, or is it the one on the left? So how many think it's the one on the right? All right, how many think it's the one on the left? A couple, okay. Well, it is in fact the one on the right. This one on the left is a total fake that we put together because the one on the right is just so boring. When you show your chips, no one wants to look at something like that and say, yes, we spent 3 years and $1 million creating this thing that just looks like nothing. So, so one of our engineers doctored this one on the left here. But again, this drives home the point, which is that it's very easy to make something that looks like it works, but much different to actually create something that works. So thanks for your attention.
Okay, time-wise, I think we're doing well. We can have a 15-minute break and come back for the rest of the presentations by the professors.
Just one question.
Yes, sorry.
So in this machine learning exercise to get the surrogate model out, were there parts of the model that were more amenable to machine learning exercise?
You said, were there faster models?
No, parts of the model. I mean, the flow, rather. Parts of the flow for the surrogate model. Were there parts of the design flow that were lending themselves better to the machine learning exercise?
Yeah, I think that's going to be a really complex answer. I think we'll have to take that one offline. But I think the short answer is, well, we're not really sure. They're all very noisy. And so most of what we've done at the current point is show just how much uncertainty there is. We're looking at the whole flow end to end, kind of like a system designer would look at it. And there are other researchers that are sort of breaking it down into individual pieces. But then kind of therein lies the problems. It's the interactions between all the different pieces that really matter. All right, thanks.